All right.
Stop telling that joke.
All right. 14.2.
Wow, and you would be like perfect favorite.
So volume, we're going to talk about volume and double integrals. So what we're going to do today is take what we've done so far with iterated integrals, finding area in the plane, our geometric interpretation of an iterated integral, and use that idea to find the volume of a solid. And our solid is going to be the solid under some function, some surface, and it's going to be bounded by the xy plane. So let's say we have a surface z equals f of xy in some region R, and I'm going to say above a region R in the xy plane. So here's what we have. We're going to draw a little picture, and we use our picture to help us out. So we have a surface, our function up here above the xy plane. So there's z equals f of xy. And here is our region in the xy plane, some region down here in the xy plane. So there's our region. So what we want to do is find the volume of the solid bounded by this region in the xy plane under f of xy. So what we're going to do is we're going to draw little, approximately, rectangular prisms here in the xy plane. And we're going to project that up onto the surface, like so. And we're going to have a little piece of this solid. Let me make this one dotted back here. Like so. And we get a little piece of this, the top of this approximately rectangular prism up here on the surface. And we're going to call this x coordinate here x sub I, because we're going to add a bunch of these up. X sub I, and back here is y sub I. And the area of the base of this prism is going to be delta x sub I and delta y sub I. So that's the area of the base of this approximately rectangular prism. And what we're going to do is sum the volume of these prisms over our region in the xy plane. So the volume of the solid under f of xy bounded by R is going to be the sum of the volumes of these rectangular prisms. So we're going to sum as I equals 1 to n f of x sub I, y sub I. So that's going to be the height of that rectangular prism, times the area of the base, and I'm just going to call the area of the base delta A sub I. Where delta A sub I is delta x sub I, delta y sub I. So this is going to be our volume, is approximately this sum. And what we want to do is make these little delta x sub i's and delta y sub i's smaller and smaller and smaller and smaller. And we're going to take the limit of this sum as that delta A sub I approaches 0. So each of our delta x sub I, comma, delta y sub I, and so delta A sub I approach 0. And just so you're aware, this idea of delta A sub I approaching 0, being a little loose with the terminology, what we're actually saying, the way that the technical way that we do it is we say that the length of the longest diagonal of any of these little elements of area approaches 0. And I'm just shortcutting that and saying that delta A sub I is approaching 0. We call that, the length of that longest diagonal is called the norm of the partition, and we're letting the norm of the partition approach 0. Essentially, we're letting delta A sub I approach 0. So we're going to take the limit of this sum as delta A sub I approaches 0, and as we do that, we're going to get the volume of that solid below f of xy, bounded by this region R in the xy plane. So I'm just going to write that out. So the volume is the limit as delta A approaches 0 of the sum I equals 1 to n f of x sub I, y sub I, delta A sub I. And as we approach this limit, we can say we're going to make this our definition. This limit is our definition of a double integral. So we write this as the double integral over R, our region R, of f of x, y, dA. So we define this limit as a double integral. So this is our definition. This is how we're going to define a double integral. Double integral is the double integral over R of f of xy dA. And we want R to, just our limitations, R is a closed bounded region in the xy plane, so we're not talking about an open region. And we're saying this double integral, this is our definition where this limit exists. If the limit doesn't exist, then that's not really going to help us. And this double integral is the volume of the solid f of xy bounded by region R in the xy plane. So we're going to say the volume equals the double integral, this double integral of f of xy dA. So this is the volume of f of xy bounded by r in the xy plane. So this is how we're going to find the volume of this solid. And we've done this a couple of times in the past where we've come up with this definition, the definition of something. This doesn't really help us evaluate this thing. This is what a double integral is. Double integral of r f of x y dA. That's this limit. We don't want to have to take this limit. We want to be able to evaluate a double integral. We need to know how to evaluate a double integral. Well, fortunately, a gentleman by the name of Fubini came up with a theorem that tells us that we evaluate the double integral as an iterated integral. So we can evaluate this as an iterated integral as long as we have a nice region in the xy plane and our function f of xy we interpret as a surface. So Fubini's theorem tells us that we can evaluate this as a double integral, or as an iterated integral, sorry. So everything that we've been doing with iterated integrals, we apply to double integrals. So if we're finding the volume, if we're interpreting this double integral as a volume of a solid bounded by f of xy in the region in the xy plane, then we can perform an iterated integral. And so what that tells us is for a less than or equal to x less than or equal to b, and just like we've been doing, g1 of x less than or equal to y less than or equal to g2 of x. This double integral over r of f of xy dA is the iterated integral a to b g1 of x, g2 of x, f of xy, dy dx. And this is for our vertically simple region. And then if we change our order of integration, if we have our region bounded by functions of y, so we're going to say c less than or equal to y less than or equal to d, h1 of y less than or equal to x less than or equal to h2 of y. This double integral over our region of f of xy dA is going to be the integral from c to d, the integral from h1 of y to h2 of y, f of xy, dx dy. And this is for a horizontally simple region. So this gives us a way to evaluate these double integrals. We've defined the double integral as this limit, and we're finding the volume of those little rectangular prisms. Take the limit as that delta area approaches 0. That limit is our definition of a double integral. We evaluate the double integral in this particular situation as an iterated integral. So questions on what we've said so far? And we evaluated a few of these, or I know we did one example, and there were some in the homework, where we evaluated this iterated integral. So now we can give an interpretation to what that iterated integral is. The iterated integral is this double integral, and we're finding the volume of a solid. Properties of double integrals mirror the properties of single integrals. Very similar. We can multiply by constant, we can add them, that kind of thing. The important properties are listed in your book on page 976. So on page 976, I go through the properties of double integrals. And they're very similar to the properties of single integrals. We can add them, we can subtract them, we can multiply by a constant, we can divide one by the other, that kind of thing.
Is anything different?
Not really. Not really. So it's just saying that just so we know that we can do all those things that we're used to being able to do with integrals. We can split up integrals into two separate integrals if we have a sum or a difference, that kind of thing. So all of those properties that we're used to using for single integrals, they hold for double integrals as well. All right, so what I want to do is go through some examples of finding volumes of solids, setting up these double integrals, and then we'll talk about a couple of questions about them. A couple of questions about double integrals right at the end. So really nothing much different than we've done. We're just putting a function inside of our iterated integral is essentially what we're doing. Be aware that you may be asked questions about double integrals, about volumes, in a number of different ways. The question might ask you to evaluate this double integral r f of x, y, dA. And you need to realize that what that's asking you is to do this iterated integral and find your region in the xy plane. It might ask you to find the volume of the solid bounded by such and such in the xy plane. That's another question asking you to do this process. It might give you the iterated integral and just ask you to evaluate it. It might give you a picture and say find the volume of this solid. And all of those things are asking you to go through this process. So there's several ways that these questions end up being asked that really are the same kind of thing. All right, so let's look at some examples. So for the first one, we want to evaluate this double integral. So this is one way you might be asked this question. Evaluate this double integral. And R is our region in the xy plane bounded by y equals 0 and y equals square root of x and x equals 4. So it's asking us to evaluate this double integral, and this is our region in the xy plane. So we're finding the volume. What we're doing here is finding the volume under this surface bounded by this region in the xy plane. So what I always suggest that we do is sketch the region in the xy plane. And our sketch doesn't have to be beautiful and perfect. We just need to be able to get our limits of integration for our iterated integral. So here's y equals square root of x. Here's x equals 4. And y equals 0 is the x-axis. And let's set this up for both orders of integration. All right, so which one do we want to do first? Vertical or horizontal?
Vertical.
Vertical. Okay, so let's do our vertical rectangle. So we're going to have the integral, and this is x equals 4. So our outer limits of integration are going to be from 0 to 4. X is going to be from 0 to 4. For our vertical rectangles, if I sketch the vertical rectangles in here, there's my vertical rectangle. Y varies from 0 to square root of x. And then I have my integral y over 1 plus x squared dy dx. Now we're not going to evaluate this particular integral, but looking at this one, could we evaluate this one? Or at least the first one? First one's pretty easy, right? We're evaluating the integral of y dy. That's a pretty easy one. And our limits are from 0 to square root of x. So that's not too bad. So this one is pretty easy. All right, let's set up our integral for horizontal rectangle. So I'll draw that one in blue. There's my horizontal rectangle. So for this one, y is varying for our outer integral from 0 to what? That point is 2. So y equals 2. So we're going to go from 0 to 2. X is varying from what to what here? From y squared to 4. I can write this as x equals y squared. So we're going from y squared to 4 here. And then our integral is y over 1 plus x squared dx dy. This one, this integral, with respect to x, the inner integral, easy or hard? Hard, because we have the integral of 1 over x squared dx. So that would be some kind of trig sub thing that we'd have to do there. So this one's difficult. So this one, when we evaluate our inner integral, we get y squared over 2 from 0 to square root of x. And square root of x squared is just x. So then we have an x in the numerator, and we have an x for our u sub for the outer integral. So this one turns out to be pretty easy to evaluate. This one is difficult to evaluate. So this would be the order. If you were setting this up, I would choose this order of integration to evaluate the integral. Because this one I would have to do trig sub first. And again, another hint, another suggestion, if it helps you to remember to keep your limits straight, you can write on your limits, I could write y equals here and y equals here to remember, and this is x equals. And this is x equals and x equals. To keep your integrals straight. And once we start doing polar coordinates, and when we start talking about spherical coordinates and cylindrical coordinates, and our integrals with those different coordinate systems, it is very helpful to write your variables and which ones are which on your limits of integration, so you keep them straight. All right, questions on what we did there? All right, let's set up the problem in a slightly different way. So for this one, we're just given a sketch. So this one, we're just given a sketch of this piece, and these points are 2, 2, and 2. And we know that this plane is x plus y plus z equals 2. And we want to find the volume in the first octant. So this is another way that this type of question might be asked. You'd be given a picture of this, and it'll say find the volume in the first octant, bounded by this. So the first octant bounded by this plane. All right. So what do we need to do here? So this plane is x plus y plus z equals 2. We need z. We need our surface z, f of z equals f of x y. So what is our surface? Z equals
X plus y minus 2.
x plus y minus 2. 2 minus
Oh, yeah.
minus x minus y. All right, so we have our function. So there's our function that we're going to put into our iterated integrals, 2 minus x minus y. We also need our region in the xy plane. So we need to sketch the region in the xy plane. So our region in the xy plane is this little triangle here. So let's sketch that region. So we know that this line here goes from y equals 2 down here to x equals 2. So there's our region in the xy plane. So we need the bounds of our region. Well, we know that y goes from 0 to whatever, and x goes from 0 to whatever. What are we going to do with this boundary?
Find the line.
Find the equation of a line. You can find the equation of a line. So what's the equation of this line?
Negative x plus 2.
Negative x plus 2. And so here's a shortcut for the equation of this line. In the xy plane, what's z?
0.
0. Z equals 0. That line is x plus y equals 2.
Oh, that's way too.
So we could find the slope. We know the intercept. We can figure out the slope. We can do it that way. But in the xy plane, z equals 0. So that line is just x plus y equals 2. All right. So let's set up our iterated integrals for both orders, and then we can choose which one to evaluate. And we're not going to evaluate these. I just want to set them up, but we're going to choose which one we want to evaluate. So let's set up our integral for vertical rectangles. So for our vertical rectangles, x is going to vary from 0 to 2, and y is going to vary from 0 to what? For our vertical rectangles. Y is going to vary from 0 to 2 minus x. Whoops. And then my function is 2 minus x minus y dy dx. Is that one going to be easy or hard to evaluate? We end up with, when we integrate, we end up with a y squared over 2 and an xy and a 2y. That's not too hard. And then we evaluate that from 0 to 2 minus x. So we're going to end up with a polynomial. How about a horizontal? So we're going to set it up for horizontal rectangles. So that's. So what is it? What are you saying, Will?
Wouldn't the vertical and horizontal both be a similar difficulty because the function is 2 minus x minus 1?
Right. So Will says that vertical or horizontal is going to be pretty much the same because this function isn't very complicated, and that's true. So let's just set it up. So our outer integral is going to be, for this one, y equals 0 to 2, and for the inner integral, x is going to vary from 0 to 2 minus y, and 2 minus x minus y dx dy. So either is pretty easy. So we can pick either. And these would not be difficult to, should not be difficult to evaluate, I'll put it that way. And like I said yesterday, I usually set it up, my first choice is dy dx, and that's just my preference. It's easier for me to think that way. But, and then if that one doesn't look nice, then I try and switch it around the other way. All right, questions on that example? All right, let's set up one more with just a slightly more complicated region. The other nice thing that's going to happen, hopefully in chapter 14, is we will get very good at drawing three-dimensional solids and finding the regions in the xy plane that are the boundaries of those solids. Solids like paraboloids and ellipsoids and those kinds of things, and visualize how they're going to be situated in space. All right, so here's our example for this one. Another one where we have a picture, and we want to find the volume of this solid. All right, and then this is y equals x. This is y equals 2. And this is z equals 4 minus y squared. And we want to find the volume of the solid bounded by y equals x, y equals 2, and z equals 4 minus y squared in the first octave. And so this one was nice. They gave us all this setup. What you will be asked to do eventually is they'll tell you the region in the find the volume of the solid bounded by y equals x, y equals 2, and z equals 4 minus y squared in the first octave. And you will need to be able to come up with the sketch and the region so you can set up that double integral. All right, question? Do you have a question there?
No.
All right, so there's our setup. We want to set up the integral for both orders of integration. So we need our region in the xy plane. So let's sketch our region in the xy plane. And I always recommend, even if we have it written out like this, just sketch a nice a little xy plane so you get to make sure you get your region right. All right, so there's y equals x, and there's y equals 2. And there's x equals 2, because I think we'll need that for our other order of integration. So our region in the xy plane, is it above the line y equals x or below? So Seth says above. So if we rotate this around, this is our region. Our region in the xy plane is going to be here. This spot over here would be over here in our drawing connect. All right, so let's set up our integrals. Let's do our vertical rectangles. So here is my vertical rectangle. So my outer integral x is going to vary from 0 to 2. Y is going to vary from what to what here? From x to 2. And my function is 4 minus y squared dy dx. That integral going to be easy or hard? That one's pretty easy. We'll just end up with polynomial. And horizontal, let's set it up the other way. So my rectangle, my horizontal rectangle is going to be here. So for my outer integral, y is going to vary from 0 to 2. Oops, not 0 to 0, 0 to 2. X is going to vary from y to x is going to vary from, did I set it up the right way? 0 to y, right? 0 to y. We're going from here to here. 0 to y. If our region were over here, x would vary from y to 2. Here we're going to go from 0 to y. And we get our function 4 minus y squared dx dy. And that one is easy, should be easy to evaluate also. Either one of these should be easy. We end up with just polynomials. All right, questions on that example? Okay, so what I have next is a couple of questions for you guys about some of these ideas we've been talking about. So let's say that R is a county in North America. F of xy is the annual snowfall at a point in R. For part A, what does this double integral represent? If f of xy is the annual snowfall at xy and r, what does this double integral represent? That would represent, we're summing the snowfall over the entire county. So this would be the, Derek says, total snowfall. So this is the volume of snow.
Is that per year? Total snowfall per year?
Total snowfall per year, total annual snowfall. All right, so how about this? What would this be? What would that be? Close. So if the double integral of f of xy dA gives us the volume, what's the double integral over a region of just dA going to give us? That's going to give us the area of the region. So what would this integral represent? Snowfall per unit area. For meteorology, yeah, that would be nice symbols on that the guys could just jump. This reminds me of another joke. So Einstein, Newton, and Pascal were playing hide and seek, and and Einstein covers his eyes and he counts, and Pascal goes and hides, and Newton draws a square around himself, and he's standing in the middle, and Einstein comes out and he says, "Aha, Newton, I found you." And Newton says, "No, you didn't. You found a Newton over a square meter. You found Pascal." All right. So for this next one, we want to approximate.
Yeah, he was way there.
We want to approximate the volume by sketching the region. So this is one of those questions where, like your old book said, where we want to try to be clever. F of xy equals 4x. And R is the region in the xy plane. Bounded by the point 0, 0, 4, 0, 4, 4, and 0, 4. All right, so let's sketch our region in the xy plane. What is this region in the xy plane? We get a square. So here's our region in the xy plane. So there's R. And now let's make a sketch of our solid, our f of xy equals 4x. So let's do that over here. So here's our region in the xy plane. Here's our square down here. What is the surface z equals 4x? What is that surface? That is a plane. How would we sketch this plane? In the xz plane, we get the line z equals 4x. Oops, I missed my spot here. And that's the corner there. So what is this solid?
Oh, is that like a wedge?
It's like a wedge. It's a triangular prism. How do we find the volume of a triangular prism? Base times height. Base times height is going to give us the volume of a rectangular prism. So what do? Base times height divided by 2. So the area of the base times the height divided by 2. So what's the area of the base of this prism? What is it? 16. What's going to be the height? Z equals 4x. So here x equals 4, so z equals 16. So our area is going to be 16. times 16 divided by 2. So this is one of those problems where, for my student a couple of years ago, would say use geometry, or like use simple geometry. Instead of setting up that double integral, use geometry. And what does this come? What's 16 times 16 divided by 2? Is it 120? 125? 128? 128? Oh wait. 128? Are we good with 128? Okay. So our area is going to be our volume. Sorry, this should be volume. Volume is 128 cubic units. All right. Questions? Okay. Homework. There we go.